Hello, good afternoon. Good afternoon, everyone. Well, for those joining us from Europe, good morning to people who are in the Americas. Um, Welcome to this webinar of SDC Verifier. We will wait a minute for everybody to join. I'll now send the reminder. So to invite and remind to everybody who hasn't joined us yet, and we will start within a minute.
Good afternoon.
Afternoon.
Hello, thanks for joining again. Okay, the reminder has been sent. We'll just wait for 30 seconds more to for people to react to this. Also, I would like to notify you that this session is going to be recorded, and we will share the recording with all the attendees and also upload it to our YouTube channel, so it will be possible to review the recording afterwards. Okay. Yeah, I see more and more people are joining. Hi, Kenny. Nice seeing you again here. Yeah. Okay. So we'll start. We'll start with a short explanation of what we're going to have here today. So I'll start sharing the screen immediately. Yep. Also, yes. So once again, hello and welcome. My name is Oleg Ischuk. I am in charge of the operations at SDC Verifier, and I'm joined here today by my colleague Patronek, who is running our marketing department. He will help me to make sure that the session is running smoothly and help me with your questions. So if you have any questions along the way, please send the message to the chat box or send a message to a Q&A box or to us directly, and you will be able to unmute yourself in the end also and ask these questions directly. This session is not going to present all the functionality of SDC Verifier and the general idea. I hope that, yeah, most people here already know what is SDC Verifier. If you are new here, please send us a message later on or visit our social media or website to learn more about the software. And we're happy to present this specifically for your needs. What we're going to speak about today is the design optimization of the FEA model with SDC Verifier. And yeah, let's jump into the action. So what we are having today, we are having a model which is built within FEMAP, but once again, I'm reminding that everything that I'm presenting to you today, it is possible to perform that within SDC Verifier interface for FEMAP, for SimCenter 3D, or for ANSYS Mechanical. So the complete functionality is available for all three programs. We are having a model which is combined beams and plates. So we have some of the beam structure on top. We also have some plate or shell modeling at the bottom. This represents kind of a mud mat offshore structure, and we have several loads applied to this model. We have couple of accelerations, gravity, and some forces apply on top of this model. I'm going to prepare the checks. Well, I already done to save time. I already did some checks for beam members, beam members, welds, and plate buckling, and we're going to review the results of this checks and also see how we can make the design better and how we can optimize our structure. So as I said, project in SDC Verifier was already created up front. All the information about FEMA model is read, and I did several preparations up front. So first of all, I combined the loads. I created 10 load sets, loading combinations, where I combined my gravity with forces in a certain way to ensure a nice results, which will give us nice numbers to work on. And I created one overall load group, which is operational conditions, which contains all 10 load sets. And these load sets are going to, envelope value of results of this load sets is going to be presented for the checks and for the optimization. So model is calculated within FEMAP with Nastron, and we can go directly into checking actions. But before that, of course, we need to determine the structural members out of our finite element model. So as I said, this model contains some beams and shells elements. And what we did to this, we recognized the beams, welds, and plates for the checks. So we can just go through this recognition. First of all, I defined all the beam members in my model. So if I go to beam member finder, by default it's one button click, and it was like 10 seconds to recognize all of these members. What we can do, we can select all of them and preview. So I'll remind you that SDC Verifier is, let's plot them with colors. SDC Verifier is determining the structural members out of your finite element model to use them later on for checking. So we have all the beam members defined in our model. The same we have for the welds. So I used Weld Finder to recognize all the welds in my model. So we'll highlight them in here. We have a certain list of welds in our model, and the weld strength check is performed for this. And then what I also did extra to this, I defined a weld size. So I not only performed the recognition, but I also defined that all welds in my model are double fillet welds with 4 millimeters weld leg. So I just selected all of them and defined a type of double fillet and 4 millimeters size. We will be optimizing this size later on, so that's why it is important. And of course, I also recognized all the panels. So list of panels, list of plates on these panels is defined within SDC Verifier. I'm not going to highlight that one as well. Then I prepared 3 different checks. So we have an AISC members check, we have Eurocode weld strengths, and we have DNV plate buckling. And we are going to select some of these we're going to preview the results of the checks, select some of the members of these checks, and we're going to try to make the design better, more effective, use less materials, reduce the plate thicknesses, or change the cross sections, and so on. So let's go through them one by one. So first one, we start with AISC member check. It consists of 16 different calculations of geometrical parameters and member checks itself. I did 2 things. I did a nice plot of the results. So if I click on preview of this plot, this is what we have as a result of this check. So we have this beam member structure on top, which has some overshoots where result is about 1. So we have this vertical rectangular shapes. We have here a small overshoot, also one more here. So we're going to adjust and to improve this design. Okay. To do so, well, also it's possible to preview the results with the table. So if I click edit on this table and fill it, we'll see what actually, sometimes it's always important to understand how your structure is behaving under this loading. So it is, I see that there is some question, but I will reply to that in the end. Thank you. What I can see here is that what are the utilization factors for each property in my model for different shapes, like axial, bending, major and minor, shear and combined, and overall maximum. And we see that certain members of the square tubes and certain members of circular tubes are not passing the requirements of the standard, and in some cases it's bending, in some cases, well, in both cases it's bending or combined. So to optimize the design, I want to improve, I want to get rid of this bad results, right? Let's focus on this overshoot, the bigger areas. And to do so, we have to go to optimization. I have a few of them already done, but I'll do them again from scratch. So we need to add a new optimization rule. And to create the rule, we click on this button to where we can add different type of rules, either for beam members, for plate buckling, for plate thicknesses, for plate element stresses, and also for weld strengths. I will select beam rule now, and here I define the parameters. First of all, based on what load I would like to optimize my design. I want to select the load group, so envelope worst situation of operational conditions. Then I need to define which parameter, which standard parameter is going to be it's going to be checked against. So I'm using AISC overall check, and I want my optimized design to fall under the limits between 0 and 1. Okay. I'm going to, my goal would be here to have as small cross-section area as possible, but still fit under the requirements of AISC between below 1. And now I'm going to select what actually I want to optimize. So I click here, and I can select all entities. I can select the parts by properties, so I can select the complete property of this beam square, or I can select material, certain component, or group from ANSYS, named selection from FEMA, the other way around, group from FEMA or named selection from ANSYS. And but what I want to do, I want to select elements on my own. So I'm clicking on this, and I'm going directly to, let's rotate it a bit. I'm going just to select a portion of elements that I would like to optimize. Let's pick 5 elements on each of these beams. So I pick 5 elements here, and 1, 2, 3, 4, 5 elements here. I'm going to optimize the design just of this 10 elements. Clicking OK. And here are the members I'm going to optimize. Next thing, I need to include possible variables for replacement. For this, we're going to use the library of shapes. And in this library of shapes, we will select a certain, let's say, pipes to reduce this. So we see that rectangular beam is not okay. By filter, we can filter out the pipes, and we can select some big cross sections, because it's we have 150 by 150. Let's say we pick this schedule pipe XXS. Let's pick 2, 2.5, 3, 4, 5, 6, 8 will be definitely safe enough, but let's pick 8 also. So I select this replacements. You can pick any cross section you want from the list of shapes that we have in the library, which is almost 7,000 different cross sections, which you can store, create a list of favorites, add your own, and so on. I'll use just this 8. So we are replacing this 10 elements with possibly one of these. I'm clicking OK now, OK again. The rule is created. And what we would do now, we would want to calculate this rule. So I'm selecting the rule and I'm clicking calculate. In this case, SDC Verifier starts to run the check for these 10 elements for all the loading combinations, well, for the loading conditions that you have selected, and calculate the results for the specific cross-section you put from the library. So it uses the original forces from the model, but it maps the shapes to a certain parameters from the library to run these checks and to see what's going to be the outcome and what's going to be the results if we replace this with others possible cross sections. This calculation depends, of course, on the amount of your loading combinations, but also on the list of possible replacements. So I don't recommend to pick all 7,000 of cross sections because it will be unreadable and it will definitely take some time. Now we have the result of this rule. I can click on it, and here at the bottom we have result table. We can see all results or optimal. Let's see all first of all. Yeah, so what do we see in this table? We see the original result, which is 1.74. And then if we replace those members with this pipe, it's going to be worse. With pipe 2.5, it's already better, but still not matching. And pipe 3XXS is already fine. And up till 8, it's extremely safe. So you can adjust the limits to pick what would be the optimal, but since we optimized by minimum area, obviously pipe 3XXS will be smallest of these and still passing the requirements of the standard. So if I select optimal result, yes, my optimal result is pipe 3XXS. And now, in my opinion, the most impressive part of this demonstration is, okay, it's nice that we know that what should be the replacement, what should be the cross-section we will need to use. But what's next? And what's next is changing the model, right? So we want to change it in our FEMA model. So that's also done within one click. I click on change model. Well, it's actually 2 clicks because you also have to click yes. We will ask you again, do you want to add this property and change your model in FEMA? You click yes. And new beam property is added. If you go to the list of properties now, you will see that here we have an optimal, well, it's visually also visible already. So we changed these 10 elements into circular tube, which will pass the requirements of the standard. And here it is, optimization of 10 elements with this pipe is done. What you have to do next is to recalculate the model and see if that's if the optimization suggested by SDC Verifier is exactly what you wanted. So we'll do that in the end of the presentation, but that's the idea of the workflow. So that's how we work with beam optimization. Let's go further and create some more. Next in our list would be, what is the next standard we have? Weld checks. Let's preview the results of the weld checks first, because there I prepared for you something different. I did the very basic thing and I said that all of my welds are double fillet welds with 4mm lag. And we see that for this model, for this particular stresses, it's all okay. We are almost not having any significant results, except this one's where it's around 0.3, 0.4. So we can save up some material and make this, well, the model is strong enough. We can reduce the size of the weld. So let's do that. The procedure is pretty much the same, but I will indicate that to you step by step. So we go to optimizations, add another one where we will optimize based on weld strength rule. Group is loading group is the same. Well, I only want to I want to define the limits also. So group remains the same. The parameter would be Eurocode weld check total overall utilization factor, but now I want my result to be slightly bigger. Let's say between 0.5 and 0.9. You can also skip these steps and just pick the one from the list that SDC Verifier will give you, or you can use above, below, and so on. I like to use this feature, so I'm clicking OK. And now I need to optimize some welds. This is the only difference, is that the interface of this variable selector is slightly different. So I will optimize one certain weld just to save time. I'm selecting this, and I'm selecting the full weld by element. Pressing OK. Weld part 79.3. Remember this number is going to be optimized. Now I will have to define the possible replacements. So we have double fillet weld. Let's do a double fillet weld, but with a weld leg of 3 millimeters add, and maybe 2 millimeters. We don't need much replacements. So that's what we're going to do. We're going to calculate it with double fillet, or no, let's do double partial. Let's do both. Double partial penetration, 2 millimeters, and double fillet weld. Okay. Two options with partial penetration and fillet weld, and with 2 and 3 millimeters weld leg horizontal. Pressing OK. Replacements are done. Again, I'm clicking OK and clicking calculate. The same procedure is going to be done for 13 elements. So you see that we selected just one element, but SDC Verifier defined a complete weld, which is where this element is located. And for these elements, for this complete weld part, we're going to calculate the possible replacements. Again, the check is being recalculated, and we will receive the result which is optimal for us in this case. You can also see which parameter is being calculated right now. Okay, the rule is having a result, and the result is, see all? Well, all of them are fine, because even within the original model, we have had the utilization factor of 0.32. But since we wanted to have it somewhat worse, we see that we could reduce our model either to double fillet or double partial penetration. It will still be okay for all of them. And since we selected to optimize based on minimum value, the optimal result that SDC Verifier will suggest for us will be this one, double partial penetration, with 0.53, since limits were from 0.5 to 0.9. And we can change the model again, since we don't model the welds and there is nothing to change in FEMAP. In this case, the weld part will be edited in our weld finder tool. So I'm clicking yes, weld has been changed, and I asked you to remember the number of that weld. I hope you did so, because I did not. We go to Weld Finder, we click on Edit, and we go to Weld Strength Settings. And here we had all of them defined as a 4 millimeters double fillet weld, but one of them 79, yes, 79.3. As you can see, now it is changed to double partial penetration with 2 millimeter weld leg. So in this way, you can define all of your welds to a certain class. If they're not passing the rules, or if they are too good, you can optimize them with SDC Verifier. Huge time saver if you have, like, well, we have here hundreds of welds in our model, but sometimes it's thousands. It's a huge time saver in terms of defining the types of welding. And the last, but very important as well, is plate buckling check, where we have a plot. And since well, you've seen that this model is not very much overstressed, our okay, I have already changed the results of the standard. To be honest, I'm not sure about this result, but let's see. I was making as an example this plate, and here we do have some result. Can I see what is the thickness of it? Has been side plate of 8 millimeters steel. Yes. Okay, so this is something really strange, but it's not the result I was expecting. But the idea would be the same. Let's just to avoid more confusion, let's optimize some of this plate because I'm not sure about this green one. So the same, what we are going to do, we are going to go to the optimizations, create the new one, and create plate buckling rule. And in this case, I'm going to optimize the plate buckling code, again falling under certain limits. Let's say between 0.5 again and 0.1. And I'm going to select possible replacements for one of the plates I select. Again, I'll select just some plate from list. I don't know their names, so I'll select it by element. I'll select by element and I'll pick this one on top because I'm not sure about these results. It's 80 millimeter thick plate, and obviously results are good enough, so we can reduce the thickness of this plate. So I'm selecting a couple of possible replacements. Let's say we will replace it with 6, with, I just have to type in the value 5, 4, and maybe 2. Yep, done. So after it is done, we click OK and we click calculate. Idea is pretty much the same. Well, yeah, you know the routine now. After the calculation is done, we are going to see what would be the results of the NV plate buckling utilization factor with the different plate thicknesses for the one particular plate that I have selected. It's 842 elements that are being optimized, but actually it's just a one plate from our recognition tool. Okay, doing 5 millimeters now. Whatever amount of time this would take, to be honest, well, I remember doing these things manually, and this is a big time saver because in a lot of cases I would have to guess. So I would have to go to FEA, change the thickness, recalculate, reanalyze, see the result. If it's not okay, I go the other way around or do the next thing. So here I can, well, you know how your structure is behaving, you know what approximately you would like to try, and then you define these replacements and see the result immediately. So let's see what are the results. So our original plate is 8 millimeters thick and utilization factor is 0.12. So we can significantly reduce this. And as you can see, it is not linear because if we improve it, so 4 is still very much okay, but 2 millimeters is already not. So we definitely can define the 4 millimeter as an optimal thickness. And in this case, probably it still doesn't fit in my limits because I set a limits from 0.5 and here we have 0.39. So I have to change this a little bit. I hope it is, well, it's very likely it's going to be recalculated. Let's say 0. Okay. Pretty sure it's going to It's going to be, yeah, I will have to recalculate. Well, let's do this. Anyway, it's another minute. While we're doing this, I will explain to you once again, and we will go through that after we update the results, that SDC Verifier is not changing the force distribution in the model. SDC Verifier is not changing the model in this case. We are just mapping the stresses or the forces. In case of beams, it's forces. In case of welds, it's also forces. In case of plate thicknesses or fatigue analysis, it is the stresses in the elements. We are just mapping the results that we currently have in our FEMAP model to the other results, to the other cross sections or thicknesses. And you cannot in this way select your complete model and let's say all the beam members on top and just update all of them, because we need to keep the force balance and distribution the same, but it helps you to update the local overshoots and pick the best decision was almost 100% accuracy. So after we recalculate it, it will be the same, but we will have optimal, and I want to impress you once again with changing the model in FEMAP. So we have a result, and the optimal result in this case is going to be 4 millimeter thickness, as I said. And if I'm changing the model, clicking yes, you would see that in our FEMAP model, we have another optimization rule, which has changed one specific plate, which we decided to reduce the thickness by 2. So it was 8 millimeters, and now it is 4 millimeter thick plate. That's it. And the last thing before presentation of the results, what you would have to do is to update the information from FEMAP, clear the existing results, and go to your standards, let's say beam members. The only thing, I had this in morning session already, is that our parameters has changed. If I click on editing the parameters, I would see that for section build type, I need to define properties to my new parameter. So I will define that this one is also rolled. The others are defined by elements, and this was the only one based on property. Okay, and now I have to recalculate this check. To do so, I select the plot and select preview. SDC Verifier starts to recalculate the check, and I remind you what we did with the beams. We had this rectangular tubes which were not completely passing the requirements of the standards, and we had about 10 elements which are overshooting. So we decided not to change all the elements, which would all of the complete member, which would be, yeah, I assume in the real life situation you would change the full member. You're not going to update few elements, but that was my creative design decisions. So as you can see now, yes, the overshoots in the places where we had it before, they still remain, but these places which were not okay, now they are fine according to the AISC rules. So now we can go update this, or maybe change the complete member, or maybe do the whatever change it is done. And I remember doing these things by hand when I was doing engineering consultancy at SDC Verifier. I sometimes spent days in guessing the correct sections, cross sections, and this one, well, in half an hour we did plates, welds, and beams. So you can imagine that this is a huge time saver for cases when you need to improve the design after the code checking has been done. That's it. That's everything I wanted to present to you today. No boring slide, just the pure functionality of SDC Verifier. And just to remind you once again, it is available also for both ANSYS, FEMAP, and SimSender 3D. The functionality is the same. I just decided to use FEMAP for the demonstration today. I've seen some questions in the chat box, and Petro, maybe you have some in the Q&A. Can you please?
Yeah, I have few questions. First one is, can I use my own shapes in the library for the beam optimization?
Yes, you can. I'm not sure if you can add them manually. If you go to settings, edit library, and there is a library for shapes, you have the list of shapes we currently have, and you can add, no, you can select it from here. The thing is, maybe you can also import, yes, you can import the shapes from Excel file. So we have a functionality we can share with you. You can copy the standard. Let's see how it works. I never did this before. Well, I'm not going to spend this 10 minutes now to clarify how to do that. But the idea is, yes, it's possible. You can add your own shapes. If you have a significant list of these shapes, you can also send it to us. We can automate this for you. We had a customer who delivered to us a list of like 300 shapes, and we did all of them in half a day. So we can automate that for you also. But using your own shapes is definitely possible. Thanks.
One more questions from my side. It's which standards are available for the optimization?
Basically, it's unlimited. What I've shown to you today, any standard that you have prepared, we have them in the list of our optimization, and you can pick any of this. So either your custom ones or the new created. So if you're creating a rule, you can pick from the standards that you already have done. It can also be a custom rule. We optimize it's more a limitation on type of checks, but it's basically the same. It can be both plates, beams, and welds. So it is unlimited. Any check in SDC Verifier can be used for the optimization, or even some of your own with custom checks. Thank you. Something else, Petro?
No, I don't have any questions. Maybe someone wants to unmute himself and ask questions or type it in the chat box. But
okay, thank you. Yeah, let me know if there is any more questions to be asked. The one more thing I would like to add is that optimization is not a part of a standard license of SDC Verifier of a professional. Optimization is a part of SDC Verifier Enterprise license. Not all of you are the users of this license, but it is obviously possible to improve, and it is possible to have this, to try this. So if you are not a user still, you can request a free trial of this. If you are a user of professional license, let me know, and I can give you, let's say, a month of a trial or so. And if you are looking for an upgrade to SDC Verifier Enterprise with optimization, it contains also the open API, where you can program SDC Verifier yourself, and some more features. So please contact us whenever you find this useful for you. And if there are no further questions, I would like to thank you for your time and for attending this session. I hope it was, yeah, I see Dennis is raising his hand. Can you please
I also
unmute yourself or type it in? Yep.
Hello.
Hi.
Can you hear me well?
Yes.
Hi, Oleg. So thank you for the presentation. I have several questions to you. So I see the workflow is that this SDC verifier, it updates like the model, and then we can recalculate, like solve it again, but with optimized results. Is the workflow is the same for SimCenter, like Siemens NX? Because the model is more complex. We have like separate FEM file, we have separate SIM file, we have a separate results file, and it is not like connected like it is in FEMOP.
Okay, I got it. Yes, SDC Verifier connects to ANSYS, FEMAP, and SimCenter in different ways. In ANSYS, we have a workbench. The idea for all three programs is the same. I have no idea how it's done within the programming part of it, but our developers managed to run it for all three programs, and it is available for SimCenter as well.
Okay.
And you got the workflow correct. Yes, you have to. We are not updating we are calculating on the original model. We are just mapping the thicknesses or shapes, and afterwards you have to update. But connection of SDC Verifier to both FEMAP and SimCenter is simultaneous. You can have it in the embed mode also, but if you're changing something in FEMAP, like I did, change the property or change the load, you just click on this update button, and in SimCenter it's the same. You can either continue with the same results or clear the calculated results, and we read all the changes in the model if something changed in properties or loads, and then we post-process the updated results. So yeah.
Okay. So this optimized structure will be introduced into FEM file automatically. Yes.
Yes, it should be. I'll check exactly. Well, I'm not that big user of a SimCenter 3D. I mostly focus on FEMAP or ANSYS, but I'll check with the developers if there are any limitations. But it is our goal that all the features are the same for all three programs.
Okay, thank you. And one more question to functionality. I see that you are setting the list of possible thicknesses. For example, is for buckling calculations, and the SDC verifier is checking each thickness. Does it fit or no? But can we set the required buckling factor, and the program will show us the thickness which fits this buckling factor?
I understand your question. Yeah, that's a nice suggestion, but we want to keep the logic the same for all of the programs. Sorry, for all of the types of optimization. If we do this with beams and we run it through 7,000 shapes, it's going to be very time consuming. And the same here. We want user to define a limitation. So you can set thicknesses with plate thicknesses, it's not that hard because you basically know that it can be from, let's say, 2 millimeters up till 20 millimeters, but not significantly more. So maybe that's something to update for the future. But for now, the idea is that all of the checks of SDC Verifier are, the final parameter is the utilization factor. It's basically comparison of the real output, either that stress or buckling factor, to the allowable value, and if it's above 1, it's not passing the requirements. But you can also do the reversed calculation. But for now, we do not suggest this idea because also users might have different requirements. Somebody wants to keep their result, as I did today, between 0.5 and 0.9. We don't know what is acceptable for you, so we leave it up for you to define possible replacements. But that's a good suggestion, so I will note that. Thanks.
Okay, and also the question, does this software identify the conflicts between, for example, buckling factor and some stress utility factor when we are reducing the plate thickness to reach some buckling factor, but at this time we are also exceeding our utility factor, for example, for a stress check?
It doesn't have any references to check the conflicts with other standards. So what I would suggest is to go to create except the plate buckling, also add a fatigue or a static stress check, and here we will have a nominal check. And then I would suggest to create a new optimization where I will check the plate elements according to the Eurocode nominal check of the utilization factors, and then running this check with the new model and see if that's actually okay, or just not even creating the optimization, but just checking the nominal where we calculate the delta stress and we calculate the allowable, take it calculate it from yield and verify if our allowable is okay or not. So it is yeah, you have to prepare a couple of codes, and in the end I still recommend to update the model and run all the checks to make to be completely sure that everything is fine. And that's easy with our reporting. So you create a template-based document where you include all the checks you want, and then it is very, very fast to change. So you do the report with, let's say, this 4 codes, stress plots. It's enough. Well, not stress plot, the utilization factor plot, right? So maybe I will very briefly add this because this is a good question. So you include the results of checks. Let's say for AISC, the general one. Well, this is not that quick, as I'll show only one, but the idea is that I will select here the load group. With default view on all entities, I will plot the utilization factor, press OK. Okay, yeah, it will take time also to calculate this. So what I wanted to present is that you prepare a template for report, and then you go to FEA map, adjust your model or do whatever you want, then go to SDC Verifier, add the update the data, calculate it once again, and generate the plot to see if there are no conflicts between different checks. But this is nice insights. Thanks for your comments and questions.
Okay, thank you.
All right. I believe that's it. If you have any further questions, feel free to reach out to me by by mail or by phone or in any convenient way. Thanks for attending this session, and I hope to hear from you again soon. Thanks. Bye-bye.
Thank you.
Thanks, Oleg.
Bye.